Hello everyone, we are group 4. Our group project is about heat effects on active transportation. Um, everyone doesn't want to live in hot environment, right? So that's why we conduct our project. We have three motivations. The first is the problem urgency. It means that it's difficult for us to know the slight killer, and the second is the human or the societal impact. The heat is very difficult for us to move around, like biking or walking. And the third is the environmental or urban challenges. It means that heat will cause traffic congestion and climate change.
Hi everyone, I'm Namin. So the overall objective of our project is that we are going to first calculate a heat index at a very high spatial temporal resolution. And then we are going to bring in the social demographic data and align them together so that we can either perform some heat mitigation scenario analysis. For example, we can explore the potential effect of bringing in the cool roof or planting more trees, or we can also perform some heat risk analysis to explore the differences in the heat exposure across different census groups. Yeah. So a common data type that is used for the heat analysis is the land surface temperature. However, like in comparison with UTCI, the Universal Thermal Climate Index, we can see that actually the LST have a very low spatial temporal resolution. So that's why in our study, we're gonna use the UTCI. And the figure left is the distribution of differences between the LST and the UTCI. And we can see that the LST usually underestimates the heat risk. That's because UTCI can estimate the overall thermal stress on the human body, taking in a lot of factors here, which are ignored by the LST. So, well, it's showing differently, but yeah. So to calculate the UTCI, we collected and preprocessed a huge chunk of environmental and climate data, and then we feed them into the SOWIC model to get the hourly UTCI at a 1 meter spatial resolution.
So I will give you a brief introduction about the Atlanta city, our case study. As many of you know, it's a bustling city, and busy city. So there is some significant challenges for transportation and stuff, and it will be hard to know biking and walking during the summer. So to measure the heat exposure accurately, we have to work with a huge amount of data set. I mean the LiDAR data set. So each tile that we were working on was around 5 million data points, and each tile was 64 megabytes. So totally for Atlanta City, we had around 23,000 tiles, and we ended up with 580 gigabyte files. So it was hard to handle those data set, and we had to extract two important key feature from that data set. One was the building data set, and the other one is the canopy data set. I mean the height of the building and the height of the canopy to measure the heat trap in the city, accurately. This is the example of our final data set. The left one is the digital elevation model, and the right one is the extracted data set. That was one of our key data set. We can run in 2 days, and finally we ended up with a building digital surface model that is the height of building in a city.
Okay. Beside that, we already use like a sky view factor that basically is a measurement of how much of the sky is visible from the ground. So this input was calculated by LiDAR data, and this is like a proportion index between 0 to 1. And at the same time, we use land cover data. What we did here was to download the data, reclassify those values, and finally we have like gray color as a concrete building and green one as a different type of land cover. And as we mentioned before, that was our initial purpose, but we went through hard um moments to estimate like this heat indicator. So to figure out the thing, we already calculated LST, is Landsat surface temperature, with 30 meter as a special resolution. And what we did here was to assign these LST values to the road in Atlanta to see how that temperature vary in roads in Atlanta. Um,
Alrighty, so in order to contextualize heat experiences in Atlanta, we also needed to understand more about the communities and their locations within the city. So you'll see here we have two maps representing socioeconomic and demographic data that we pulled from the American Communities Survey as part of the US Census. So on the left, you'll see household income with darker values representing higher income and lighter values representing lower income. And the red circles indicate the downtown Atlanta area. So you'll notice that high income areas are clustered predominantly in the northern and northeastern parts of Atlanta. And then on the right, we have a map representing the percent white population in the city of Atlanta. And you'll see that there are similar patterns to the map on the left, in that areas that are a higher percentage white areas are located again in those northern and northeastern areas of Atlanta. And so you'll see strong patterns between both household income and race represented in the city of Atlanta. So next, we wanted to take our understanding of some of those socio-demographic factors and overlay them with the road network that you saw earlier. And so you'll see the road links are represented by the lines on this map, and the top 10th percentile household income is represented in blue, and the bottom 10th percentile household income is represented in red. And those are intersected again with those road links. And what you'll notice is that when we compare the mean land surface temperature in the top 10th percentile household income links and the bottom 10th percentile, we find a difference of about 3.2 degrees Celsius, which is about 6 degrees Fahrenheit. So even within just the city of Atlanta, which is a large city, but is still only a city, you see a large range in the temperature difference that folks are experiencing. And again, we found a correlation between the land surface temperature and household income of negative 0.3, meaning that as household income increases, the land surface temperature in those areas decreases.
About the- So about the challenges, I can say about we had a limited time to handle those amount of data set that I mentioned. It was around 580 gigabyte data set, and I mentioned the LiDAR dataset. It was take lots of time to download, move it to the HPC and those stuff. So we have a limitation of amount for or and for the LiDAR dataset. The problem that we had was handling projection and alignment because these were the point data sets. So the projection of each point will be take lots of time. So we were handling to run through the night, but unfortunately, one of the challenges that we had, one of our batch files was wrong, and we missed some of our data. So we had a pivot at that time, and we chose to use the land surface temperature rather than the UTCI.
In addition to the huge data sets we are using, we also have a very complex model and pipeline. So in order to set up the environment, we really had some difficulties like accessing the correct content environment paths. And Nathan, a special thanks to Nathan, that really helps a lot. Another thing is some bottlenecks in our pipeline takes several days to execute. So we also did parallel processing to like enable the time efficiency of the pipeline.
So for the takeaways, we we are more familiar with the iGuide platform and Envy platform. Also, in our group, we talk to each other, help each other, and know each other better.
Some of our other key takeaways were determining when to pivot and when to try different approaches, which we did many times. And then also making sure to do regular data sanity checks, especially with coordinate systems, and making sure everything is projected the way that we want it to be.
Okay, so next we want to express a special thanks to the Nathan and Kunji. They helped me to solve the technical problems. Thank you so much. This time. Okay, so the question is, was this a ton of fun? No, we don't have plenty time to sleep, so every day we are so sleepy. But but it's still a very wonderful journey for us. I want to say, like, as long as I think I will live this afternoon, I was so sad. I want to cry, but I don't have this ability to cry immediately. By the way, thanks so much for providing this valuable opportunity. Thank you so much.